Hi, this is Barrett Givens, and in this video, we're going to talk about a theorem about the closure of a set A that will help us when we're trying to find closures in examples and homework problems. So this theorem will be useful for us to figure out what the closure of a set looks like. Okay, so the theorem says, let A be a subset of a topological space X. Then Y is in the closure of A if and only if for every open set U, if Y is in U, then U intersect A is not empty. Okay, if Y is in U, then U intersect A is not empty. So, all right. Let's just rewrite that in a couple different ways to make sure that we understand kind of what comes after the if and only if on here. Let me highlight that. So this whole bit here. So one way that I can rewrite that is I can write it using the contrapositive. So I can say equivalently, Y is in the closure of A if and only if for every open set U, if U intersect A equals the empty set, then Y is not in U. Okay, I just took the contrapositive of this if-then statement. So that would be another way that we could phrase it, and that might be useful. All right, and then let's also just draw a Venn diagram because this one is a little bit hard to grasp all at once. So the idea is, here's my set X, here's A, and if Y is already inside of A, well, we know A is a subset of the closure of A, so that's easy. So let's kind of imagine that Y is maybe not in A, okay? But it should be sort of close to it. So maybe Y is right here. And what we're saying is that no matter how small of an open set, no matter what kind of an open set we take, if we take an open set that has Y in it, that open set has to overlap with A a little bit. If we take an open set that has Y in it, it has to overlap with A a little bit. That's what the highlighted blue thing means. If we take an open set U that has Y in it, then that open set must touch A. Okay? So let's go ahead and prove this. Proof. This is an if and only if, so we have to go two directions. Forward direction. Suppose Y is in the closure of A. Suppose Y is in the closure of A. Well, that means Y is in the intersection of all closed sets containing A. So that means that if it's in the intersection, that means it's in all of them. So every closed set containing A, Y has to be in it. Okay? Now we want to prove this property in blue, or we might want to prove the equivalent contrapositive form of it that I'll highlight over here in purple. Either way, the thing that we want to prove starts with an arbitrary open set U. So let U be an open set. So I either want to prove the blue statement, which is where I assume that Y is in U, and then I prove that U intersect A is non-empty, or I want to prove the purple highlighted statement, which is the contrapositive, where I assume that U intersect A is empty, and then I show that Y is not in U. Um, let's do the purple one. Let's do the contrapositive one. Okay. Assume U intersect A is empty. Since U is open, U complement is closed. And since U intersect A is empty, A is a subset of U complement. Okay, U intersect A being empty is equivalent to saying that A is a subset of U complement. So these two statements are equivalents of each other, two different ways of saying the same thing. All right. So now U complement is a closed set which contains A. That means that U complement is one of the sets being intersected to form the closure. So by definition of closure, of Y being in the closure, we must have Y an element of U complement. In other words, Y is not in U. Okay, so I assumed that U intersect A was empty, and then I showed that that meant Y would not be in U. I assumed that U intersect A was empty, and then I showed that Y is not in U. And so therefore, assuming that Y is in the closure of A, I proved this blue highlighted statement. Technically, I proved the purple highlighted statement, but they're equivalent, so that works. All right, now the other direction. Okay. I either want to suppose the blue statement or the purple statement, either the original statement or the contrapositive form of it. And I haven't quite decided yet, okay? So let's just leave a little space here. Assume that for every open set U, I'm going to decide what I'm going to write there in a little bit. Just put a period at the end of that sentence that is not yet completed. Now we want to prove that if this property is true, that if we have this element Y and we have this property is true, we want to show Y is in the closure. What does it mean to be in the closure? To be in the closure means that you're in the intersection of all the closed sets containing A. To be in the intersection must mean that you're in every single one of them. So I want to show that for any closed set containing A, Y is in that closed set. So let's let F be a closed set containing A. Okay? I have to show that Y is in F. And since F is an arbitrary closed set containing A, that would mean that Y is in all of them, which means that Y would be in the intersection. So let F be a closed set containing A. Let F be a closed set containing A. Then F complement is open and F complement intersect A is empty. Let's draw a picture. So here's my A. Here's a closed set F containing A. And then F complement is what's outside of that. So F complement is the part that's outside. So F complement is out here. Okay. And so we can see that F complement doesn't overlap with A at all because A is entirely inside of F. Okay. So this is my F complement right there. All right. F complement is open and F complement of A, F complement intersected with A is empty. So now I really like this form because I have an open set intersected with A being empty. So let's go ahead and write that at the beginning of my proof. Assume that for every open set U, if U intersect A is empty, then Y is not in U. Okay. So, all right. So I assumed my purple hypothesis. I said, let F be a closed set containing A, just any closed set. Then that means F complement is open, and F complement satisfies the first part of this if-then statement. F complement intersect A is the empty set. So this, if this, then this is true. So by hypothesis, Y is not an element of F complement. Well, if you're not in F complement, then that must mean you are in F. So Y is in F. But F was just an arbitrary closed set containing A. So without knowing anything about it other than that it was a closed set containing A, I was able to show Y is in F. Thus, Y is in every closed set containing A, which means it is in the intersection of all closed sets containing A. But if Y is in the intersection of all closed sets containing A, well, the intersection of all closed sets containing A, we have a name for that. That's the closure. So Y is in the closure of A. Okay, that proof, I feel like that proof is pretty tricky to just kind of like track where you are. It just feels like I'm making one statement after another and it's hard to see the flow of it. And so you might want to take this proof and kind of write it line by line, and then maybe on like one side of your page, and the other side of your page, try writing like why each line is true, and also drawing Venn diagrams. I drew a couple of Venn diagrams, but I think that this is one of those situations where like a Venn diagram at every step might really help you to understand what's going on. All right. Thank you for listening.